So in last lecture we had finished up with this example looking at the binding energy of iron 56, one particular isotope, and there were the numbers that we had come up with. So taking a look at the iron, we got a total mass of the protons, neutrons, and electrons here. Then we looked up iron 56 mass in Appendix F and subtracted that to find our missing mass. And then we took the atomic mass units representation and converted that into a certain amount of energy. And so the energy conversion from mass, 931.5, there's a point right there, MeV, and that left us with 492.3 MeV total. So that's a total number, we boxed that, that's an important result. And then we also reported this in terms of per nucleon, 8.790. Now there's another example here, down in the corner, and that's actually this example that's given in the slides. It says, what's the binding energy of the last neutron in carbon-13? And I'm glad there's a question mark there, because at first I looked at this and I thought, what do you mean? How do you pick out just one neutron and figure out what its binding energy is? But I think what they're meaning by this, and there's a homework problem that reads kind of the same way. What they're saying is, let's compare carbon-12 and carbon-13, because they really just differ by one neutron. Now, we saw with carbon-12, on average, the binding energy per nucleon in carbon-12 was about 7 MeV per nucleon. So let's see what happens if I think of this reaction. Let's think of starting with carbon-12. There is its mass. And I don't have to look up carbon-12's mass in Appendix F because it's exactly 12. And then I looked up the neutron's mass. And then I looked up the mass for carbon-13. So what I'm thinking of is I'm going to run a nuclear reaction here. I'm going to start with carbon-12 nucleus. I'm going to bring one more neutron in and have it join together with all of the other protons and neutrons that are there. And I want to see how much energy is released in that particular reaction. So if I combine the mass of a neutron and a carbon-12, and then I'm going to compare that, so I added those together, and then I'm going to compare that with carbon-13, what I'm actually going to do is subtract this. And what I'm finding is when that neutron comes in, it's an explosive, energetic process. It's not like the neutron just kind of comes in and sticks, and that's the end of the process. The mass has actually gone down by 0.00531 atomic mass units. Well, if the mass has gone down, that's telling me a lot of energy was released when that neutron came in. And we can use our 931.5 conversion. It says that 4.946 MeV of energy was released when the neutron came in. So that energy release, it could be a high energy photon. I'm guessing that's the most likely thing. So this gamma energy photon, really high energy photon, is given off when the neutron comes in. So again, these protons and neutrons are not like marbles that just stick very passively. When protons and neutrons rearrange themselves in these nuclear states, huge energy differences take place. So the additional neutron released about 5 MeV. So it's saying carbon-12, on average, the binding energies were about 7. This neutron that came in only has a binding energy of about 5. So it's going to lower the overall average. And it's saying that, carbon-13, on average, probably has a binding energy per nucleon a little lower than carbon-12. And those are the kind of calculations that you can do. So you can add a proton or a neutron at a time and ask how much effect did that have on the overall binding energies. All right, when we look through the periodic table, we already had one diagram that kind of showed us how this worked. What we could do is we could go through the periodic table, and for each element, we could create a table that shows the possible number of neutrons. So that's what we've done here. So let's just explain what's going on in this table. Along the horizontal axis, we have the number of protons, and that says if I look at each value of Z, it's a different element. So along here, you know, Z equals 1, that's hydrogen, Z equals 2, it's helium, Z equals 3, 4, 5. Where was iron? Iron was like element 26, so iron is like in this vertical column. Tin was like element 50, it's out here. Uranium was like 92, it's out. So the horizontal scale is showing us where all the elements are showing up. And then along the vertical scale, it's saying how many neutrons there are, and each point corresponds to a stable nucleus. So if we look at the stable combinations of protons and neutrons, what we find is this. We find out that from hydrogen all the way up to element 20, which is calcium, that the most stable isotopes are the ones that have equal numbers of protons and neutrons. So you think helium-4, carbon-12, oxygen-16, calcium-40, those are the most stable isotopes. And the argument here is, if you remember our wave function argument, there was kind of this a set of 1s states. Now the nuclear states don't have the same energy pattern that the electron states have, and that's because the nuclear force behaves differently from the electromagnetic force. But if you think of this in terms of different quantum states and pairings of protons and neutrons, that if I start to build up an excess of neutrons, for example, it turns out there are reactions where neutrons can turn into protons. So if there's a bunch of lower energy states on the proton side, neutrons can turn into protons. On the other hand, if I'm building up an excess of protons, some of those protons can turn into neutrons. So that keeps the numbers sort of similar, at least early in the periodic table. Now the second effect that's coming in is that the protons are repelling each other electromagnetically. So through the electromagnetic force, the protons repel. The neutrons don't have that issue. So if we think of looking at the energy states of the protons and the neutrons, the energy states on the protons are going to be spread out more than on the neutrons. Even though there's two effects here. One of the effects is kind of to first order, similar numbers of protons and neutrons, but then we have to recognize that the neutrons, we're going to need a few extra neutrons compared with protons. The neutrons are giving us a little more binding energy than the protons are, because the protons are all positively charged and they're all repelling each other. And that's what we see in the periodic table. So as we go through the periodic table, at first that one-to-one effect is dominant, but as we move through, what we see is that we want to pick up just a few extra neutrons, and then a few more, and then a few more. Now by the time we get to the end of the periodic table, those differences are pretty significant. So I'm looking at element number 80 and seeing that they might have 100 or 110 neutrons. That's a lot of excess neutrons compared with the number of protons. But that's the general trend we see. As you move through the periodic table, you're always needing just a few more neutrons than protons to provide the most stable isotopes. Now, what would happen if we don't have those stable numbers? And again, there's different processes that can take place, and we'll be looking at those. We can have radioactive decay take place. So we can have a neutron turning into a proton, or a proton turning into a neutron, or we can have an, what's called an alpha particle, a small chunk breaks off from the nucleus. So this is just, it's a lot of words. It's just pointing out that the nuclear force, the strong nuclear force, is short range, it works in the distances of femtometers. So the strong force doesn't extend out like the electromagnetic force. What they're referring to is the Coulomb force, or the electromagnetic force in nature. It's long distance, but the nuclear force is not. So let's move on into radioactivity. So I guess we are now headed in towards these questions of which isotopes are stable for an element and which isotopes are not stable for an element. And we can take a look and see how those work. So this is talking about Marie and Pierre Curie and the discovery of polonium and radium, elements that were radioactive. Historically, it was identified there were 3 different types of radioactive decay taking place. Some could barely penetrate a piece of paper, some could get through a small amount of aluminum, others could go through a bunch of lead. Those got named alpha, beta, and gamma. Again, here's these different types of radioactivity in a magnetic field. Whatever the alpha particles were, they were positively charged. Whatever the beta particles were, they were negatively charged. Whatever the gamma particles were, they didn't have an electric charge to them. So these were kind of the clues that researchers were seeing with these different types of radioactive decay. So they could identify these high energy particles coming out. So let's look at these individually. So for alpha decay occurs when we have 2 protons and 2 neutrons that separate off from the rest of the nucleus. So the example they're providing here for alpha decay is radium-226. Now if I start with radium-226, that is element number 88, and it has 88 protons and it has 138 neutrons. So you can see that excess of neutrons that we were talking about. Radium-226 is unstable. It undergoes radioactive decay, and it undergoes the alpha process. And in the alpha process, a helium nucleus, 2 protons and 2 neutrons are given off, and that's actually what's referred to as the alpha particle. So the alpha particle, the high energy particle that shoots out from this nucleus, actually consists of a helium nucleus. It's a very stable combination of protons and neutrons. Now, what that means then is if the radium-226 shoots out a pair of protons and neutrons, what's going to be left are 86 protons and 136 neutrons. So we've gone from 138 neutrons down to 136, 88 protons down to 86. And so we've had a drop in mass of 4. So that's an example of an alpha decay. Now, where are the electrons in all this? And you're thinking, well, I know that the radium started off, if it was neutral, which is likely, it started off with 88 electrons. When these decays occur, the alpha particle leaving probably does not take any electrons with it. It's leaving so fast, it has so much kinetic energy, there's not time for electrons to pack their stuff and head out with them. The electrons get left behind. But what we'll see in some of our energy calculations is that we often just assign the electrons there anyway. We'll see an example like this in a little bit more detail, but that's kind of their outlining of alpha decay. Now, they have a notation for this alpha decay, which I always feel like is a little confusing. So you have to kind of stop and see what they're saying. It says you start off with some nucleus, and it's got this mass, and it's got this number of protons. And then what happens is it turns into some other nucleus, they're calling N prime. The top number is going to drop by 4. And the bottom number, the number of protons, is going to drop by 2. And then what's going to come out is the alpha particle. And that alpha particle is being written as helium-4. I kind of like that. Instead of just writing alpha, they've written it as helium-4. So that's the pattern that we see in alpha decay. Now here's an example that we can take a more detailed look at. This example is saying all the isotopes of uranium are radioactive. None of the isotopes are stable. Once you get past a certain point in the periodic table, once you get past lead and bismuth, there just aren't any more stable isotopes of anything. And so all the isotopes of uranium are radioactive. Here's one of those isotopes, the 232. Now they're giving us the mass number, so we don't have to go to Appendix F and look this up. They've written this down from Appendix F. 232, and again, it's not coming from the periodic table, it's coming from a list of isotopes. And I'm specifically looking up the 232 isotope. 232.037156, yes, I get to keep all those significant figures. And it decays into thorium-228, I gotta look that one up too, 228.028741. Take this, subtract off the mass of the helium, and we'll see how this energy calculation carries out. So here we are. Just a quick reminder, we've got 3 different types of radioactive decay. Right now we're looking at alpha decay. In alpha decay, a helium nucleus is given off, and this is how I diagram it. So here's my uranium-232 converting into thorium-228, and then here is this high-energy helium being given off, so that's my squiggle line means high energy. Now, why is it that the helium gets so much energy and the thorium not so much? And it's because the helium's much lighter. So if we think of this in terms of this diagram right here. So here's my uranium-232. Let's imagine we have a nucleus of uranium-232, and it's just sitting there, it's at rest, and it undergoes radioactive decay. Well, that would say that a helium-4 shoots out in one direction. But since momentum is conserved, if a helium-4 shoots out in one direction, something's got to shoot out in the other direction, and the only something we have is the thorium. So, I don't know if you guys remember, this should look familiar from special relativity. We looked at some examples like this, and now what we can do is we can kind of drag out our formulas that we used in special relativity and apply those formulas to the situations that we've got here. So I'm going to say mass 0 is the mass of the uranium-232 we start with. I'm calling mass 1 the mass of the thorium, and mass 2 the mass of the helium-4. Now again, we're kind of playing fast and loose here with the electron masses. We're just going to treat these as all neutral species to simplify the process. So here it is. These are the 3 masses that I looked up in Appendix F. And I want to take the mass that I started with, M0, and subtract off M1 and M2, those masses, and this is the missing mass. So what we're seeing for this radioactive decay process is I've got missing mass again, like I did before. Now, I can take the amount of missing mass, 0.005813 atomic mass units, and find out what its energy equivalence would be. And the equivalent amount of energy would be 5.415 MeV. So that's how much energy is released in this process. Now, we refer to this as Q for these reactions. So it's kind of like in thermodynamics when we said Q was heat. So you can kind of think of it in the same way. What it is Q is going to be the combined kinetic energies of all the products. So when we release a bunch of energy in these nuclear reactions, the energy is going to get divided up between the products. And so in this case, we only have 2 products. We've got the thorium coming out, we've got the helium coming out, and the thorium is going to have some kinetic energy, the helium is going to have some kinetic energy. Let's step back. We know how much energy total is available, but let's step back to special relativity and remind ourselves, for a problem like this, how do we determine how the energy is going to get divided up? So coming back to this slide, for alpha decay, here's the problem that we're currently taking a look at. We have this uranium decay into thorium and alpha decay. So the other piece of that will be a helium nucleus that's coming out. And so just stepping back a couple of slides here, we outlined that here. Here is the uranium, it's splitting into two pieces. There's a thorium piece, there's a helium piece, which is the alpha particle. And we want to go in and determine of the available energy, the 5.415 MeV of kinetic energy that will be generated by this decay, how much of that goes with the thorium, how much goes with the helium. And we've looked at this in special relativity, so let's step back to that and remind ourselves how we had derived some of these equations. So back in special relativity, we had looked at this example, something with some kind of mass splitting into two pieces. The mass of the two pieces is going to be less than the mass of what it started from. That decrease in mass will show up as kinetic energy. So the conservation equations we want to write down here are that energy is conserved, so the mass that we start with represents all the available energy for the two particles. So the mass of the object at rest is going to become the energy of the two particles. Now, notice that I don't have the factors of c squared here, and that's to save an enormous amount of time in the algebra. So when you're doing all of these relativity equations, the m's are mc squareds, the p's are pc's. By not writing the factors of c, it's going to save us a lot of time. And so it's kind of standard. It takes some getting used to. But what I'm going to do is I'm going to use this shortcut technique of anytime I write m, it really stands for mc squared. And anytime I write p, it really stands for pc. Now what that says is our standard energy formula, E squared equals PC squared plus MC squared squared, simplifies down in terms of writing to E squared equals P squared plus M squared. Again, it takes a little getting used to, but let's see if we can use that approach. So instead of writing MC squared, I'm just going to write M naught and understand that at the end of the problem, wherever there's an M, I just put factors of C back in. That's how it will work. So energy conservation says the energy in the mass that we start with is going to get divided up between the two particles. And then the second item here is momentum conservation. This is just in one dimension. So whatever momentum object 1 picks up, it's going to have to get matched with object 2. They're going to have equal magnitudes of momentum. So I'm going to write P1 equals P2. Now I've got two equations with too many unknowns. So what we can do is, for these momentum expressions, we're going to come back to here and write those momentum as E squared minus M squared. So let's do that on each side. So in place of P1, think of these as squared now. P1 squared equals P2 squared. Well, that's equivalent to E1 squared minus M1 squared equals E2 squared minus M2 squared. And now I've got these two equations to work from. So now I have two equations and two unknowns. The idea in a problem like this is all the masses are going to be given, let's imagine. So they're giving us M naught, they're giving us M1, they're giving us M2. I can look up the masses of the uranium, the thorium, the helium. So the only unknowns are the E1 and the E2. Now what we could do then is take this equation and let's come up with an expression for E2 right there. E2 would be equal to M naught minus E1. So in the next line I've substituted that in. And so what we've got going on here then is E1 squared, down to the next line, E1 squared minus M1 squared doesn't change, but on this side, the E2 is being replaced by this expression. Now I'm down to one equation with one unknown, and I want to go in and solve for E1. So I multiplied this out, and then was able to cancel the E1 squareds, and now we're down to the only place E1 shows up is here, and then there's a couple lines of algebra, and what I end up with is E1, the amount of energy that the object 1 or particle 1 ends up with, is given by 1 over 2 m naught squared plus m1 squared minus m2 squared. And let's see, here are all the m squareds in the algebra, and I'm paying attention to the signs to get those correct. Now, the energy of object 2, looking at the equation that we solved for E1, I don't necessarily have to go back and solve all of these expressions. What I can do is I can look at equation 1 and say, look, the problem we set up is symmetric. It's symmetric under exchange of numbers 1 and 2. It was arbitrary that I called this particle 1 and this particle 2. I should be able to switch the 1s and 2s and get the very same formula. And that's what I've done here. In place of 1, I'm writing 2. In place of 1, I'm writing 2, and in place of 2, I'm writing 1. And so it gives me these sets of equations, E1 and E2. And we can check. We can do a quick check and see do these energies seem to work. And if I add these two equations together, let's see, I have a common factor of 1 over 2 m naught. If I add these two equations together, the m1 squareds cancel, the m2 squareds cancel. I'll have 2 m naught squareds divided by 2 m naught, and it says, yeah, if I add these two equations together, that takes me back to m naught. So these look like they're the right equations. Now, for our purposes, I think this is as far as we went back in special relativity. What we would like to do is, starting now from these energy equations, let's derive one that specifically has to do with kinetic energies. So let me pick up with equation for E1 and say that the kinetic energy of particle number 1, nucleus 1, is given by its total energy minus its mass. And so what that would be is I have an expression for the energy right here. So I've written that down. And then from that, I need to cancel out or subtract off m1. Now, in order to keep a common denominator, here's my m1 expression right here. I want to be able to keep a common denominator with the energy expression that I've written. So I added factors of 2m naught above and below, and that gives us some common denominators. So I can factor the 1 over 2 m naught out. Doing that gives me a kinetic energy formula 1 over 2 m naught. I now have an m naught squared plus an m1 squared minus 2 m naught m1. Well, that factors into the square of m naught minus m1. So I've combined terms in my factoring. I've got this m naught minus m1 squared, and then the final step in all this is to recognize this is the difference of two squares. So if back in your calculus classes and your math classes you loved manipulating all these factors around, this is a perfect sort of derivation of our formula, because now I can take these difference of two squares and factor that out into m naught minus 1 minus m2, m naught minus m1 plus m2. So I've factored that back out again, and I did that intentionally because m naught minus m1 minus m2, well, that's our missing mass. So that's actually equal to q. So this part of the expression is going to get replaced with q. And down in that final line that we have right here, I have the k1, I still have that factor of 1 over 2 m naught, times Q times m naught minus m1 plus m2. And then the final version of my kinetic energy formula is right here. That K1 is equal to Q times m naught minus m1 plus m2 over 2m naught. So the 2m naught got brought back inside. And the nice feature of this is that the energy units I can think of as being contained in the Q. And so the masses, I don't necessarily have to put the factors of c squared back in. If I do put the factors of c squared back in, they cancel out in any case. And so this actually works pretty well in terms of kinetic energy. Let me just adjust the projector just a bit. All right, that helped. So you can actually see equation 2 now. So I've got K2 is the same formula with the 1s and 2 subscripts replaced. So those are the kinetic energy formulas. Again, what is it we solved for? We have to think about how the problem started out. The idea was that if I start with an object with mass m naught and it divides into 2 pieces, m1 and m2, how much kinetic energy will each of those particles have? And we've conserved energy, we've conserved momentum in order to come up with those 2 equations. Okay, we've got our equations. Let's go back and apply them to the problem at hand here. And the problem at hand was uranium-232 decaying into thorium-228 and helium-4. And I went to Appendix F, not a periodic table. Don't go to the periodic table in chapters 41 and 42. We got to go to Appendix F and look up the masses. Here's the mass of the uranium-232, mass of the thorium-228, mass of the helium-4. That's my alpha particle. And then just apply the formulas. So the formulas we came up with, I'm going to call thorium particle 1. That's what I've done with the masses. So the kinetic energy that goes into the thorium is my Q value. Now Q we had already calculated at 5.415 MeV. And then this, it's Q times this function of masses. Now that also conceptually is a nice way to think about this. That amount of whatever, calculating all that mass factor, is going to tell me what fraction goes with particle 1, the thorium, and how much goes with particle 2, the helium, or the alpha particle. All right, so I substituted all those in. I have 9 significant figures on some of those numbers. I'm paying close attention. I don't want to get any of those numbers wrong. And when I substituted these in, I got 0.0173 and 0.9827 as the 2 fractions of Q. How does the Q get divided up into kinetic energies for each of those 2 particles? So those add up to 1. That's a good sign. So we've accounted for all of the Q. And it's saying that because the alpha particle is lighter, you can see that from the formula here, it's going to be the lighter particle that picks up more of the kinetic energy, and by the amount described by these formulas. And so it's looking like the thorium is going to pick up 1.7% of the Q is going into the thorium, and 98.3% is going into the helium, or the alpha particle. So in terms of MeV, that's 0.0935 MeV for the thorium, 5.32 MeV for the alpha particle. Now, we know enough special relativity, we could even carry this out one step farther. We could go, okay, if this is an isolated reaction and there's a decay and these things come shooting out, how fast are they going? So we could go in and calculate some velocities for these. So let's try that. Now I'm going to use relativity formulas. It turns out that the speeds here, especially for the thorium, they're not extremely large. They're not so close to c. But let me go ahead and use relativity anyway. So I got gamma as 1 plus kinetic energy over mass. So for the thorium, the way I'm going to calculate its gamma factor is 1 plus, now this is the kinetic energy that we calculated for the thorium. And in the denominator, what I want to come up with is an energy number for mc squared. And I can get that energy number by taking the 228 atomic mass units and multiply by 931.5 MeV. Now, maybe you're thinking, well, wait, can I round off to 3 significant figures? Absolutely. What we're trying to do is maintain 3 significant figures of precision. I got 3 significant figures here, 3 significant figures here, got 4 significant figures here. We're fine. So what does happen is I've got all these extra significant figures on these masses. The only time I have to use all of them is when I'm subtracting 2 numbers that are very similar to each other. If I'm just multiplying numbers, I don't necessarily need all these significant figures. I can round back to 3 or 4 significant figures. It's only during the subtraction process, when we're trying to find small differences between 2 numbers, that we have to have that level of precision in the values. So anyway, what I've done is I've been able to write the mc squared for my thorium in terms of MeV, and then the MeVs will cancel. And, well, the gamma factor is almost 1, 1.000000440. That's barely enough that my calculator can maintain, 3 significant figures of precision at the end. So there's 3 significant figures of precision at the end of my definition of gamma. That was barely enough to carry me through the calculations. And, oh, the rest of it's right here. So now that I've got the gamma factor, I can solve for V using my formula from special relativity, and it's telling us that we're moving at 0.000938 times c. So it's about 1,000th of c. And we've gotten so used to having things travel near light speed. At first we might be thinking, well, how fast could that possibly be? Well, that's pretty fast, 281,000 meters per second. So the slow-moving particle, which it's easy to get the impression that when something decays, the large piece that's there after the decay is basically still at rest. Well, it's not at rest unless you consider 281,000 meters per second as being at rest. So the thorium comes shooting out of this reaction too. Let's do the same calculation though for the alpha, because that's the one that we're thinking is really going to be moving fast. So for the alpha particle, for the helium-4 coming out, same calculation, 1 plus, now here is the kinetic energy. And remember, most of the kinetic energy, 98% of the kinetic energy is going into that alpha particle. So here's the amount of kinetic energy that comes out in the alpha particle, the 5.32. I'm taking its mass, 4.0, multiplied by 931.5. That'll put me in MeV. Now again, every isotope of every element is going to be accurate, reasonably accurate to 3 or 4 significant figures just by assuming its integer value. So we don't have to keep all those extra significant figures if we're just doing multiplication. Anyway, that gave us a gamma factor. So the gamma factor on my alpha particle is 1.001428, and the speed that we end up, 0.05338 times c. So the alpha particle is going about 5% of the speed of light. Okay. And carrying out that calculation then, and I need to lift up my projector again, that's going at 1.6, 10 to the 7 meters per second. I'll lift this up a bit. Okay. So you can see this is going at a really good clip. The alpha particle is really moving at a high speed here. All right, so these kind of calculations, I do feel like we've done these in chapter 37, I guess it was, special relativity. This is a good chance for us to come back and really utilize some of those formulas. So pay attention to these examples. This is a really good example. All of this alpha decay stuff that we've looked at here is pretty useful. All right, let's move on and say just a couple more things about alpha decay. When a nucleus decays through alpha okay, so energy is released in alpha decay. I guess the question they're asking here is, this is similar with quantum mechanical questions, right? Is why doesn't, if something's unstable, why doesn't it just decay? Why does it wait? And then, if it is going to wait, well, why doesn't everything decay after the same amount of time? There's a series of different times at which these will decay. So if I have a bunch of uranium-232 nuclei, and I pay attention to, I'm watching all of these, they don't all decay at the same time. You know, here's one decays, one over here decays, one over here decays. And the way we think about that is, well, first of all, it's a quantum mechanical effect. And so we've got wave functions representing all the protons and neutrons inside that nucleus. Now, there's a strong force that creates a barrier holding all those protons and neutrons together. But there's a possibility, so we can calculate a certain probability that some of those particles in the nuclei could find themselves outside the range of the strong force. Remember, the strong force is only over a short distance. So the wave functions are going to spread outside of that range. Now, there's some probability then that some protons or neutrons could end up outside of the nucleus. Now, what happens then is, in order for a decay to take place, there would have to be a lower energy region that the alpha particle can tunnel into. So the idea is everything's staying together, but at some point there's some probability that this separates, and by separating, that's going to allow the possibility of releasing energy. So that's what happens. So, you know, one way to think about these radioactive isotopes is, it's not that the radioactive isotopes are unstable, it's that there's something else that's even more stable, which is not very difficult to get to. So there's a different combination of protons and neutrons that's more stable than what we have right now, and there's an easy way. If there's an easy path to get there, then there's going to be a probability of getting there. And the probability says there's no way to determine individually when the nuclear decays will take place, but we are able to predict statistically at what rate the decays will occur. If we have a large sample, we can monitor or we can calculate over time how many of those decays will take place. So this is kind of modeling that sort of an effect. So alpha decays, not every alpha decay has the same lifetime. Some of them, some isotopes have longer lifetimes or half-lives. Some alpha decay materials have shorter ones, and that depends on the barrier that's been set up by the strong force and the stability, the relative stability between reactants and products. This is just pointing out that, I don't know if these smoke detectors are still around. It used to be that there was a period when most smoke detectors had a little bit of americium, a radioactive material, inside, and it had a detector. So you got a little bit of radioactive material in these smoke detectors, and then you have something that watches for the alpha decays. And if the smoke gets thick enough, it interrupts the alpha particles. The heliums get stopped by the smoke particles, and they don't reach the detector built within the smoke detector, and the detector goes off. It says, I'm not detecting any more alpha particles, something must be blocking their path, and it's the smoke particles. All right, we want to move on and take a look at beta decay. So we've looked at alpha decay. We now want to take a look at beta decay. And for beta decay, let's look at an example here. This is carbon-14. This is a radioactive isotope of carbon. And again, it's not that carbon-14 is unstable. It's just that there's something that carbon-14 can turn into relatively easily that's even more stable. So it turns out that nitrogen-14 is more stable than carbon-14. And there's an easy path that takes us from carbon-14 to nitrogen-14, and it's beta decay. Now, this shows that we have an electron and a neutrino that are given off. So in these decays. And the electron is really low mass, and the neutrino is really, really, really low mass. And that means that they're going to carry away most of the kinetic energy in these reactions. Let's look at take a closer look at this. Now, what it's saying here is that the electron that's produced here, that's not an orbital electron. That's a new electron that's being generated. It didn't exist until the decay itself took place. So here's the example. Let's go ahead and outline this. So here's the carbon-14. It's decaying into nitrogen-14, and it's calling it beta emission or beta decay. All right, here's what I want to get to. So beta minus decay, and the beta minus is telling us that there's actually different versions of beta decay. There's a beta minus, there's a beta plus, there's a beta neutral decay. So 3 different types of beta decay. The ones that were first identified are these beta minuses, and for most naturally occurring materials that beta decay, it is beta minus. But now we know of hundreds, maybe thousands, of different isotopes that beta decay. So we know about, anyway, let's take a look at this particular process, and then we'll see how the others are related. So here's carbon-14. It turns into nitrogen-14, and what you're thinking is, well, wait, if I've got carbon turning into nitrogen, those are different numbers of protons. Now, what's happening is there's an underlying reaction. So this is how I'm going to suggest you think about what's going on, and when you're doing these problems, write down the reaction that's being observed, but then underneath in parentheses, I'm going to write down, here's what's really going on. What's happening is a neutron has turned into a proton. Now, we've kind of hinted about that a few times already, and now we're seeing an example of where a neutron, it's kind of like there's too many neutrons around. Let's turn one of the neutrons into a proton to get a better balance between protons and neutrons. So a neutron turns into a proton. Now we're going to bring in a little bit of particle physics, fundamental particle physics, elementary particle physics, which we'll see in chapter 43. Here is what's called a Feynman diagram, and this is through what's called the weak force in nature. So we think that there's a strong force, there's a weak force. They often show up in nuclear reactions, so we think of them as a strong and a weak nuclear force in nature, and it's distinct from the strong force. The weak force applies to all types of particles, not just protons and neutrons. And what the weak force does, the weak force actually enables particles to change their identity. So early on in the course, I think we wrote down protons and neutrons. We said they're really similar particles. They're kind of the neutral and positive version of the same particle? Well, it turns out that the electron also has a neutral partner, and it's called the neutrino. So protons and neutrons can turn into protons can turn into neutrons under given circumstances. Electrons can turn into neutrinos, or neutrinos can turn into electrons. That's also possible. Now what's happening in these beta minus decays is a neutron is turning into a proton. Here is the weak force. So again, these are Feynman diagrams, and in chapter 43 we'll be outlining all sorts of reactions using these diagrams. What the weak force does is it enables the neutron to turn into the proton, but it requires that at the same time another pair of particles have to change identity. And in this case, the change of identity is that an electron and a neutrino. Now in this example we're looking at, instead of having an electron come in and turn into a neutrino, we're actually generating an electron and a neutrino at the same time. And what we understand from fundamental particle physics is that's a possibility of creating a particle and an antiparticle. So what's happened is we've created an electron and its neutral partner, an anti-neutrino. So you're thinking, wait a minute, neutrinos, they're neutral, how can we have antiparticles? And we have antiparticles of many neutral particles. They're antineutrons. And we'll get more into that. They have reverse properties. Even though they're neutral, there are other properties that are reversed for these antiparticles. So what's coming out of this is an electron and an anti-neutrino. And it comes from that fundamental reaction right there. All right, so counting everything up, I got 6 protons, 8 neutrons, and 6 electrons going into the reaction. I got 7 protons, 7 neutrons, 6 electrons coming out. Now, the 6 electrons that went in are going to come out as spectator electrons. This other electron that we have right here, that comes shooting out of the reaction. That is not part of the nitrogen-14. Now, if all I have for the nitrogen-14 are these 6 electrons, that's not going to be enough. The nitrogen that comes out is going to be missing an electron. So I just want to make sure that we charge balance this reaction to make sure we're getting everything taken care of correctly. So in order to have the nitrogen charge balanced, we're going to need to assign it a plus sign. Now, when we come down to calculating Q, how much energy is actually getting released in this reaction? The Q for this would say, hey, start with the mass of the starting material. So we're going to start with the mass of the carbon-14, and then we subtract off the mass of all of the products. Whatever's coming out of the reaction, we've got to add together all of their masses. So let's see, what's coming out of this reaction? Well, there's a nitrogen-14, but it's missing one of its electrons. And then there's an electron, and then there's an anti-neutrino. So I'm going to list all of those. Now, let's first of all consider the neutrino. The neutrino's mass is really, really low. The electron-neutrino system it's not so much like the proton and neutron system. The electron mass, or the neutrino mass, is really tiny, probably less than 1 eV. Neutrinos are difficult to make measurements on. We still don't have definitive masses, but we kind of have an idea of how much mass they could have. And so it's easily possible that the electron has 1,000,000 times as much mass as a neutrino. All right, in any case, that means that we are just going to ignore the neutrino mass. And then if I take the mass of an electron and add it to the mass of nitrogen, missing an electron, well, the combination of that is the same as the nitrogen mass. So it turns out in beta minus, in order to take account of the masses before and after and count all the electrons properly, we take the mass of the carbon, the mass of the nitrogen, and look those up, the mass of a neutral nitrogen, and then just take the difference. The difference here is 0.000167, and the Q on that is 0.1556 MeV. Okay, and it's outlined over here. Mass of the neutral carbon that we started with, mass of a neutral nitrogen, which includes the electron that's shot out, plus the nitrogen that's produced in the reaction. There's the difference in mass. Oh, look, the arrow's pointing right at it. Multiplied by the 931.5 MeV to give us our value. All right, I think we're coming up on time to stop for the day. So I'm going to do that. I'm going to stop here. In the next lecture, we'll pick up from here with beta decay, and then we'll move on and look at different types of beta decay.